Hello, everyone. So welcome back. So in this section, we talk about mutation testing. So what we learned so far, so we learned how much code can be covered by test cases, right? So we have a quantitative measures to measure the coverage, test coverage. So the question is, do the coverage metrics directly measure the effectiveness of test cases? Do 100% coverage or like 90% coverage actually means you have a very good test case and your program is bug free? So answer is no, right? So the coverage metrics do not directly measure the effectiveness of test cases. Then how to determine whether a test case or a set of test cases are effective? Okay, so why we need test cases? So we want to use test cases to either to verify the correct behavior of our system or detect incorrect behaviors to find bugs, right? If we have two test cases, so one test cases find more bugs than the other one. So we can see the one finding more bugs is better, right? So if test case A can detect more bugs than test suite B, then we say A is better than B, right? The best test suite can detect every bug. Whenever a bug is introduced, at least one test case will fail. Then we can find this bug. Then this is a good test suite, right? But in fact, we cannot ensure that we detect every bug, right? Because we don't know how many bugs we have in our program before we run a test. Even after we run a test, it's impossible to find all the bugs. Okay. So how to measure test suite effectiveness? The simple way is to find all the bugs in the software and to evaluate how many test cases. So how many bugs our test cases can find, right? This is a way to evaluate the effectiveness of our test suite. As I said, we don't know how many bugs are there, right? It's either only after we run a test case that we see the bugs, right? So we cannot use this number of bugs to evaluate test cases. Okay, so this is like a chicken or eggs dilemma, right? So you cannot, before test, you don't know how many bugs. Even after test, you don't know how many bugs. And you cannot find all the bugs and then evaluate the effectiveness of your test cases. Then how can we evaluate? We say either test coverage is not a direct measure, and also we cannot find all the bugs and do a direct measure. How can we measure the effectiveness of our test cases? So one way is, or the state of the art solution is to artificially inject bugs. We artificially will add bugs to the correct program. Then, so we know we inject bugs, and our test case should be able to find these injected bugs. If our test cases cannot find the injected bugs, we need to update, we should add more test cases to find these injected bugs, right? This is the solution, or like we call it mutation testing. What is mutation testing? Actually, modify or mutate some segments in the source code so that we have many different versions of the code. Each version is just one mutation to the original version. So this version is a bug because it mutates the original source code. So something is wrong. So it is a bug. So our test cases should be able to find this bug. We check if the test case can find the bugs. Some test cases should fail the bug. Some tests may not fail, but at least some test case should fail the bug to find the bug, right? So this is a called mutation testing, and this is how we can evaluate the effectiveness of our test cases. Okay, so mutation testing is fault-based testing, right? So we add mutations, we inject bugs. So uh, we use our test cases we run our test cases to see if we can find some typical faults that could occur in our program. So this typical faults is we artificially inject those typical faults. Okay. So basic idea is we take a program and the test data generated for that program, right? We take a program and test cases, and we create a number of similar programs. So each similar program is a mutant. Each mutant is different from the original program in one small way, right? For example, we change one plus sign to a minus sign as shown in this figure, right? Which original one is a equals to b plus c. You can change it to a equals to b minus c. So we have another mutant. We have a mutant. This is another program. This is a buggy program. Or we can change a equals to b plus c to a equals to c plus c. So this is another mutant. We have two mutants here, right? So each mutant is slightly different from original program. Okay, the original test data is then run through the mutant. So we run test through the mutant. If test data detects all differences in the mutants, if we find a test case failed, right, then the mutant are said to be dead because we found this mutant. So our test case is good, right? It can find these bugs. So these mutants are said to be dead. And we say the test case is adequate. Okay. So mutation testing is not a testing strategy like equivalence partition testing. It doesn't outline test data selection criteria. It's a way to evaluate the effectiveness of your test case or your test strategy. So it should be used in conjunction with traditional testing techniques, not replacing them, okay? So steps in mutation testing. First step, so we modify the statements in a code and create mutants, like we create small changes, right? We create a big number of mutants. Each mutant is just a slightly varied program. Then we run the test cases and we run the tests against this mutant, okay? And compare results of the original and the mutant, right? The test case should find a difference. The mutant is killed if different results are found, right? The test case is good as it can detect this change. The mutant is alive if the results are the same. The test case is not effective. If we have a mutant, consider it as a bug. But if our existing test cases cannot detect this difference, cannot detect this bug, so our test case is not sufficient. We need to add more test cases. Okay, and the mutant is alive, and we need to add more test cases to kill this mutant. So a mutant can live in two ways, right? If a mutant is not killed, if it's alive, there may be two possible ways. Either it's because the mutant is equivalent to the original program. Sometimes we change something, but the behavior program doesn't change at all, right? You can write the program in different ways, but it's still correct and it's exactly the same. So this is equivalent mutant, right? So no test case can kill the equivalent mutant because there's no difference between this mutant and the original program. Another possibility is that the test set is inadequate to kill this mutant. This mutant is a bug, but your test case is not sufficient to kill it. Okay, two possibility that a mutant remains alive. Okay, so in a later case, the test case need to be re-examined and updated, and then to add more test cases to kill the mutant. How to generate this mutant? We can either manually generate this mutant, right? We just manually look at the code and we change like one small sign to another sign, right? Do small changes, but it's not so efficient, right? Usually we use automated generation of mutant. In fact, we use a mutation operators. Each mutation operator is to change, is to apply some small change. Okay, use some rules to apply some small changes. There could be different mutants. The first one, stillborn mutant. These mutants are killed by compiler. You change the part of the program, but the program is not, it cannot compile anymore as a stillborn mutant. It's killed by the compiler. Second, trivial mutant. It's killed by almost any test case. Right? You change something and significantly wrong, and every test case can find it. That's a trivial mutant. And we have equivalent mutant, always produce the same output as the original program. Right? And none of the above are interesting from mutation testing perspective. We don't want this. What we want to have mutant that represent hard to detect faults, right? A good mutant should be hard to detect, should represent some faults that your existing test cases may not detect, okay, or hard to detect. So there are some examples of mutation operators, and you can look at a more complete list following this link, okay, below. There's some examples like statement deletion. You can delete a statement, right? Or statement duplication. You can just duplicate a statement. Replacement of Boolean expressions with true or false, right? So those are simple mutants. Or change a sign, right? Change a plus to a minus. Changes greater than to greater and equal than. Okay. So these are some examples of mutation operators. And there are also some mutation operators specific to certain programming languages, like specific to object-oriented programming languages, like replacing a type with a compilable subtypes, right? That's one mutant for object-oriented programming language. So there are some assumptions, right? So what about so here we just change a small part, a small sign, or remove one statement or duplicate one statement, right? Just small bugs, right? What about more complex errors involving several statements? Our mutants do not cover those complex cases, right? We just make some small changes. What about these more complex errors? Can our mutant represent those cases, right? The answer is there are a couple of assumptions, right? The first assumption is competent programmer assumption. The assumption is that a programmer, an experienced or competent programmer, when they develop a program, the program can be either correct or differ from the correct program by a combination of simple errors. So experienced programmers either make correct programs or make small mistakes. They don't make big mistakes because the small mistakes are easier to ignore, right? So they make small mistakes or simple errors. Competent programmer assumption. The second assumption is a coupling effect assumption. So basically, the more complex the errors can be detected by a small error, actually. What does it mean, right? So the test data that distinguish all programs differing from a correct one by only a simple errors is so sensitive that also implicitly distinguishing more complex errors. if a test case can find a simple error, so it can also find a more complex error. That's a coupling effect assumption. Okay. So when we run the mutation test and we use the default specification, we can specify what mutation operators we want to use. Okay. Basically, ideally we want to run all the mutation operators, right? And we want to represent all the realistic types of faults. But the problem is there may be a very large number of mutation operators, and the generated mutations will be very big, and it's very time consuming and resource consuming to run the test case against all the mutants, right? So we can specify which mutant we want to run, right? And also we can specify which test cases we want to cover. And we have this mutations of this mutant. So how can we measure the effectiveness of our test cases? So we want to make sure that our test case can find this mutations, can detect this difference, right? Can find those bugs generated by mutations. But how to quantify it, right? So our approach is to use a score called a mutation coverage, right? So mutation coverage or mutation score is a ratio of dead mutants over all non-equivalent mutants, right? Ideally, we should kill all the non-equivalent mutants, but in fact, we may just kill a part of them, right? So the ratio of dead mutant over all non-equivalent mutant is called a mutation score. The higher the mutation score, the better the test cases, right? Then here, so specifically, formally, the mutation score is equals to 100 times the number of dead mutant divided by the number of mutant minus the number of equivalent mutants, right? Okay, let's look at a simple example here. Original code here on the left. Some mutants, what mutant we can have? First one, we can change the mean value equals to A to mean value equals to B, right? A small change. Then we have a different version of the program. A second version, we can change B, the leaf condition from B smaller than A to A smaller than B, right? There's another mutant. Third mutant is similarly. Fourth mutant, we add one more method call, right? Fifth mutant, we change the assignment to mean value, okay? We do one change at one time, okay? And then we have this another mutant as well. So here we look at, we see that mutant 3 is equivalent, right? Mutant 3, because A is assigned to mean value in original program, the leaf contains B smaller than A, and we change it to B smaller than mean value. But A and mean value are the same. So the third mutant is equivalent to our original program. So we call it an equivalent mutant, okay? Yeah. So in order to find an appropriate test case, right? So we must to ensure the test case can reach the fault seed during the execution, right? So it's a reachability. So we need to make sure that our test case reach the certain line, right? For example, reach the mutant, the code line of the mutant. And another is infection. A mutant should cause the status of program to be incorrect. That's the injection. Third one, is that a mutant would cause the program, the output of the program to be incorrect as a propagation. Okay, so here we have these three definitions in order to define our two types of mutations: weak mutation and strong mutations. Okay, it's let's look at the strong mutation. What is a strong mutation? What is weak mutation? The strong mutation is a fault must be reachable, infected state, and propagated to the output. Right? If we want to kill a strong mutation, right? So we need to make sure that so the sorry, for strong mutation, it means a fault is reachable, the fault infected state, and the fault is propagated to output, right? So this is if we want to detect the difference between a strong mutation and the original code, so we must ensure that the outputs are different. Okay, a weak mutation, so it doesn't have this propagation part, right? A fault which kills a mutant, it only be reachable and infect the state, right? It only needs to reach this line and change the state of the program. It doesn't need to propagate to output. So this is a weak mutation. So it's easier to kill a weak mutation, right? So here is it's a definition of a strong mutation coverage, right? How to strongly kill mutants. So given a mutant M for program P and the test case T, right? T is set to strongly kill M if and only if output of T on P is different from output of T on M. So only the outputs are different, test case can kill as mutant. Okay, but so here we have a strong mutation coverage. It's defined based on this strong mutation definition, right? For each mutant M on M, the test requirements contains a test case which strongly kill M. That's a strong mutation coverage. And similarly, we have a weak killing mutant and weak mutant coverage. It's just so that they just remove the output part. Okay, so let's look at an example. That's easier maybe. So here in this example, we look at this mutant, right? So here we just change the fourth line, right? We change the mean value equals to A to mean value equals to B. This is our mutant. So here, reachability, right? It's easy to reach. It's unavoidable. It's reachable, right? And the infection, if infection, so we want to change the status of the program, right? If B is not equal to A, right, then it's infected. But if B is equal to A, this state of the program doesn't change, right? Mean value equals to A equals to mean value equals to B if A equals to B, right? So if B is not equal to A, then this status is changed. Propagation, we need to make sure that the output are different, right? If B is bigger than A, right? If B is bigger than A, then we will not go to the branch of if B is smaller than A, right? And if B is bigger than A, then we see the difference. If the two programs will have different outputs. For example, if A equals to 5, B equals to 7, right? So in the first program, it would returns 5, but second program, it will return 7, right? So that's a propagation, right? But if A is bigger than B, right? We change the status of our program. We change the also it's reachable, but the outputs are the same because if A equals to 8 and B equals to 2, right? The program on the left would return 2. The program on the right will also return 2, right? So it's not propagated. If a test case find this, if a test case specify a equals to 8 and b equals to 2, you cannot see the difference in the in output. So it's actually a weak mutation. Okay. So any questions here? Okay, let's continue. Another simple example, right? This is in this example. So we will see how to test a program and how to generate a mutant, how to run the mutant, and how to update our test cases in order to kill this mutant. Okay. So this program is very simple. It's actually the program prompts the user for a positive number in a range of 1 to 20, and then for a string of that length, right? The program then prompts for a character and returns a position in a string at which the character was first found, or a message indicating that the character was not present in the string. The user has the option to search for more characters. So here, if you have a look at this program, right? Basically, you first specify a length of the string, right? Then you input that string within that length. Then you give a character, and then the program automatically finds the location of that character, right? Let's look at the test case, right? The test case, first, we see that the x is the length of the string, a is a string, c is a character, right? The response is either if you want to do another search or not, right? And the output is on the right, expect outputs. Okay, so first, if we input 25 to x, so the output will be input integer between 1 and 20, because we only accept input between 1 and 20, so 25 is not correct. Then we input 1, right, as the size of the length, and when you input x, it's okay. The size of the string is 1, and the string itself is x. And then we input the character x, and then we find that the output is the character x appears at position 1, right? And then the response is yes, we want to another search, and then we put another character a, and the output is the character doesn't occur in the string because we only have x in the string. Okay, and response n, we discontinue, we stop it. Okay, this is a simple test case, right? This is our existing test case and our existing program. The next, we want to evaluate the effectiveness of this test cases. Okay, so how to do it? We do mutation testing for sure, right? Mutation testing, we just do one change here. Found equals to false, we change to found equals to true, right? Then the found will be equals true, and then we'll never enter a loop, okay? And the result is true. We found something, right? So what happens? We run the original test case data, right? This test case data, we do the same thing. We run it. And then we find that the result is character A appears at position 1, right? We found the next time we input A, right? We input X is fine, it's found because the found is true, it's always true. And if we input A to find the character A, it's still true because found is always true, right? It's incorrect. So this mutant is detected by our test case and is killed. Okay. This mutant is killed. We don't need to update our test case. Next, we do another mutant. Here, x equals to size of A, we change it to x equals to 1, right? And we run our original test data, right? And here, but it cannot, it's still correct. So our result is still correct. Because there in our original test data, we only find the length of the string is only one, right? So we only need to run one. And here we change the x to one, and it's always one because our test case string, the set of string is one, right? So it doesn't matter, it's still correct. But this program is not correct anymore. It's an incorrect program. It's a buggy mutant, but our test case cannot detect it. So what we can do, right? We need to modify our test case to identify it. What do we do, right? We add a new test case here. The size of the string is 3, and we put XCV, three character string, right? Then we do it, and we find the program is not correct anymore. It found this incorrect behavior because the string X is changed to 1, but X is actually should be the size of A, right? This is how we detect it, how we update our test cases. Okay. But here, specifically, when we find a V, right? We find the capital V, we cannot find it because in a program that the length of the string is always set as 1, so we cannot find a V, but we should find a V, right? So we update this test case and we find this problem. Okay. Another mutant. So we change from each time we would increase, we would go move to the next character, right? But we change it. We move 2 steps. So when we look at this, when we check our test case cannot find it because our test case never detect we either detect the first one or the third one, right? So move 2 steps is okay, right? It doesn't skip anything in our test case. But in fact, the program is incorrect, right? How can we augment our test case to kill this mutant? Think about it. Okay. If you have an answer, to tell me. Like, either raise your hand or put it in chat. Okay. How should we augment our test case to kill this mutant? So what we can do, right? We can just add another test. We just the same string XCV, but we find C, the second character, right? Then the change the program will show a different because the chamber cannot find the second program, right? Second character, but our original program can find the second character, right? Second character is C. So we update our test case to reflect to kill this mutant. Okay. Okay, so this is a mutation testing. So to summary, so mutation testing to measure quality of test cases. There's a basic assumption. If the software contains a fault, there will usually be a set of mutants that can only be killed by a test case that also detect this fault. So we can use this mutant to measure effectiveness of the test cases. And also provide a tester a clear target. We should kill all the mutants. Okay. But it's a computational intensive because we have lots of mutations, right? And there's another problem, is like equivalent mutant are practical problem. It is in general an undecided problem. Remember, when we calculate the mutation score, right, we need to exclude those equivalent mutants because you can never kill equivalent mutant, right? Because this mutant is equivalent to this original program. And how to determine which one is equivalent mutant? That is a problem. So nowadays, what people do, people is use a static analysis to apply some rules to compare them. This is a equivalent mutant, and but it may not be 100% accurate. Okay. there's some discussion point. So mutation testing, as we mentioned, is usually suitable at a unit test level, because we change the details of this unit, right? We change a small part in the program. But nowadays, so people have a research to run mutation tests on integration level and the system level. Okay. Mutation testing is also a useful way to assess the effectiveness of test strategies. So you have different strategies to generate different test cases, and which strategy would have a higher mutation score. That can determine which test strategy is better, right? And how to run mutation testing here. So one tool is using the PIT or PI test tool. So it's a real-world mutation testing tool. It's a state-of-the-art mutation testing system providing standard test coverage for tests for Java and JVM, and also provide a mutation coverage, and it's fast. So, so here there's a tutorial to run this PIT test for a simple program. It's very easy. So I post it here, I put it here, and I want you to do it. And I think as the time is we're not very early. So I leave it to you to run this, to put this tutorial. Okay. So it's easy. So first you make sure your Maven is installed and you clone a sample project. And in the sample project, there's a POM file, right? POM.xml file for Maven. You just check the PI test plugin there. You don't need to make changes to have a look, and then run Maven clean test, and it will generate run a test and generate a mutation testing report. You can find it there in your target folder, and you look at the file and check the mutants for each file, and check the mutation coverage as well. And then I want you to use a similar approach to run mutation testing for a real system for OpenMRS. It's for the similar approach, okay? And you can evaluate the effectiveness of the test cases of the software system.